Quite loud. All right, good afternoon, everyone. Welcome to Private Line Seminar today. I don't know why everything's going back there. Right. Yes, well, with the pleased to introduce Marc today. He is with us from Australia, from CSIRO Mining. Those of you who are in the field, you know that CSIRO is at the forefront of doing a lot of mining research. Marc is here to tell us about it, and maybe if you want to introduce us with a little bit of your background, that would be fantastic. Thanks.
Thanks, Jamal, for not just hosting me over the last couple of days, but and giving us such a fantastic representation of what you're doing here at Mines, but also for the opportunity to present to you today. I assume there must be a microphone here, so please let me know if I'm not speaking in the right direction or.
You hear?
Yeah.
Good.
Yeah. So yeah, my name's Marc Elmouttie. I work at CSIRO in Brisbane in the Mining Technologies Research Program. My background is actually, I started out in astrophysics, very different to mining engineering, and joined CSIRO about 22 years ago. Started working in the exploration geophysics area there. We were actually working on a project, quite a large project at the time, Anglo De Beers funded project to build a gravity gradiometer using an alternative technique to what one of the competitor companies was using. So we took that technology as far as we could. We discovered a lot of interesting physics, just not ore bodies. So that project came to an end, and I moved over from the exploration part of the research unit through to the mining research unit. So I've been in mining research now for about 17 years. Initially, I focused my research on developing vision-based systems for mine characterization. We actually commercialized one of the first photogrammetry systems for geotechnical mining called CSIRO Vision. And then I moved more into probabilistic, reliability-based structural modeling. So I spent quite a lot of my career developing techniques based on discrete fracture networks to characterize rock masses for both surface and underground mining, ground control. And then the most recent part of my career has been focused on sensor fusion for slope deformation monitoring. And I'll talk a little bit about that today. So just see if that works. I need to click on the arrow. All right, so I'll just a quick outline. I'll give a bit of an introduction to the Australian mining scene, just for some of you that are not familiar with it. Also to CSIRO. I'll focus on the mining research that we do at CSIRO. And then I'll cover a few different topics: design and simulation, sensing and monitoring, navigation and excavation, and human health and environmental sustainability. And then finally, I'll just touch upon some space mining, if you like, or beyond terrestrial, a bit of aerospace work as well. Having just visited the fantastic space research facilities here today, I think it's quite topical. So just for those of you who are not familiar, so Australia is quite privileged in a lot of ways. We're only 26 million people living on a continent which is so well endowed with some of the most critical metals, minerals needed for the energy transition. This graph shows you basically the Australian ranking in terms of EDR across a number of different minerals and resources. And then also in terms of actual mineral production rates, Australia is also ranked very highly across a number of those critical resources. So just for those of you that can't read the bottom axis, we go from bauxite, iron ore on the left, all the way through to tin and phosphate, but the critical minerals are there, the rare earths are there, very high ranking. And of course, we are very well known for our metalliferous and thermal coal deposits as well. However, we also have a long heritage in mining, and so we've managed to achieve quite high safety standards. This is something, by the way, that's not well appreciated in Australia. So if you ask the average person in Australia what they think of mining, they would flag it as a high risk occupation. But actually mining, you can see these statistics are based on Safe Work Australia, the governing body to monitor safety across different industries. Mining is down on the list when compared to things like transport, construction, agriculture. This is both in terms of fatality rates as well as insurance claim rates as well. So there is a sort of a misconception, distorted perception of mining being high risk. In fact, mining industry in Australia is extremely vigilant when it comes to health and safety. That's not to say that ongoing technology developments are not needed. So that's kind of the positive side of things. The negative side of things are we do face some challenges in Australia. So what you're seeing on the graph here is the share of manufacturing in terms of gross domestic product for various regions and countries. So once again, I'm not sure if that's showing very clearly on the screen, but you can see there's been a general gradual decline across domains as other industries, finance, insurance, kind of take up some of the slack. But Australia has really dropped quite dramatically, and we're now sitting just about 5% of our GDP is in manufacturing. So there's been a coring out of the manufacturing industry in Australia. And why is that relevant? Well, it's relevant because there's kind of three pillars to a modern society. There's energy, then there's the resource utilization or extraction, and then it's what you do with the resources. And if you don't kind of have that continuum, there's a disconnect. And my theory is that one of the reasons why a lot of people in Australia, we actually struggle to recruit mining engineer, like to see the success of mines here and just the quality and the number of students coming through here is very heartwarming. In Australia, it's a different story. And as I said, there's a challenge to encourage people to go into the mining industry. And I think it's because there's a disconnect, because what Australia does is we extract the resource and then we ship it offshore. And that changes your whole mindset in terms of how you value and view mining. There's also other challenges, and these are not unique to Australia, but what you're seeing here is the plan for Australia to accommodate the energy transition. So the vertical bar there is based on 2024, and it maps all the way out to 2050. And it shows you all the endowments that we're going to use to power the Australian economy from an energy point of view. And what you can see is Australia is going through a massive transition. The current plan is for Australia to scale down its coal-fired power generation quite dramatically and quite quickly. That doesn't mean we're not going to export it. And between coal, oil, gas, uranium, by the way, we have no operating nuclear power plants in Australia, even though we have the best endowments of uranium. So our natural advantages towards powering the future economy are not being utilized, will not be utilized going forward as we go through this energy transition. So the big sort of players here will be rooftop solar, which is up the top here. My mouse isn't showing, but rooftop solar on the top, then utility solar, onshore wind, offshore wind, and then down here, that black solid line, that is dispatchable capacity. So that's non-intermittent power generation that will be there on tap when you need it. And what you'll notice is that Australia's going to perform quite a big experiment in terms of the fraction of dispatchable capacity over total capacity is going to be quite small. And that poses big challenges. And then that dispatchable capacity, a big part of it is going to be formed by coordinated energy, basically through household batteries and electric cars. So the plan is for the population, I guess, to plug in their cars, plug in their batteries and provide that firming power. So this poses big challenges for us going forward, but it's not unique to Australia. So we need to obviously extract the resources to go through this energy transition. And this is from the International Energy Agency. And these are some of so what you see is everything is being shown in units of kilograms per megawatt produced. And it starts off with offshore wind at the top down to natural gas. So in terms of the amount of resource that you need per megawatt produced, you see as we transition through to the intermittent sources, there's going to be a rapid need for scale up in terms of resource extraction for some of these critical metals and minerals. That is somewhat.
How we rate the
Sorry?
the wind power?
So wind is both off. So Australia has the program in Australia is largely based on onshore wind along the east coast and massive amounts of offshore wind in the southern areas where we get those
Kilogram per kilowatt.
per megawatt.
Oh, the wind.
Oh, this is like, for example, for the turbine capacity. Yeah. And yeah, this is somewhat in counterpoint in Australia, and this is not unique to Australia, but mine approval times are actually growing. They're not shrinking. So we kind of have this conflict here of the need to tap into these resources and in faster time than previously to support the energy transition. But because there's a lot more challenges in terms of achieving social license to operate, let alone legislation, those times are actually blowing out. That's not unique to Australia. And then finally here, this context, this is once again from the IEA in terms of their forecasts for demand increases. This is out to 2040 relative to 2020. And this is the red dots are stated policies from international governments, and the blues are what would be needed for the sustainable development scenario that they've mapped out to achieve less than 2 degrees Celsius warming. So whichever way you cut it, it's a massive challenge. And so Australia is part of that challenge, and we're not going to solve it alone. And international collaboration is fundamental to getting there. And so everything I'm about to show you has been through collaboration. Nothing that I'm showing you here in terms of the research that's been conducted has been solely CSIRO developed. A quick snapshot, these figures are a little bit old, but sort of high 5,000s in staff numbers, currently 50 sites spread across Australia. I'm based in Brisbane, which is on the east coast. Mineral resources research is spread across several sites, both east and west coast. As I said, we work in collaboration with the university sector, both Australian and internationally, as well as SMEs, governments, NGOs, and the ultimate kind of goal is to make sure that this research ends up in the industry. And commercialization is one of those pathways. I'll just point out a couple of initiatives that are happening at the moment. So there's something called the Australian Critical Minerals R&D Hub, and that brings together CSIRO with ANSTO, that's the Australian Nuclear Science and Technology Organisation, as well as Geoscience Australia, as well. So those sort of government agencies in collaboration with the universities and industry sector to try to address these forecast bottlenecks in terms of critical metals and minerals going forward. And that is a current a major initiative that the Australian government is supporting. And it's also an opportunity for collaboration. Another couple of examples of technologies that have sort of had impact in the industry. One is called Nextdoor. So this uses, this was developed by one of the research programs in minerals, and this uses magnetic resonance technology, as in the equivalent to medical MRI technology, to excite atomic nuclei, but the frequencies are targeted for specific species. In this particular case, they've been targeting a copper, chalcopyrite, residing copper, for conveyor belt sorting. So this is a pre-concentration technology. This is now commercialized through this entity called Nextdoor, and they've scaled it up now to a haul truck bulk sorting system. So same technology, larger scale. The goal is to try to perform your pre-concentration as early as possible to then make those benefits in terms of both energy consumption as well as opportunities for waste utilization as well. And then the other one, actually, visiting Edgar Mine today, I found out that Emerson had scanned that mine as well. So Emerson, that's a CSIRO technology that actually that is a spin-out technology in that case. So those researchers actually spun that technology out and formed Emerson, and that's basically a simultaneous localization and mapping algorithm to use LiDAR to map real-time mapping for both geological, geotechnical, underground stope, underbreak, overbreak, so many different applications to that technology. So CSIRO is the National Science Agency. It's divided up into a number of different research units. I'm from the Mineral Resources Research Unit, but actually we collaborate with some of the other research units depending on the problem at hand. So if it's, for example, problems to do with understanding mine-water interaction or dealing with legacy tailings and waste, we will interact quite closely with environment. They have a lot of expertise in groundwater modeling, contaminant transport, those kinds of things. If it's to do with mine automation, robotics, we'll interact with Data 61, which has the robotics expertise. So there's a lot of close interaction across those research units. And we, Mineral Resources, it's about 330 staff spread across different sites. So we divide up our research in terms of these different research programs. We have characterization, and Alan showed us through some of the mines characterization laboratories here as well. So they focus on characterization from the grain scale, the lab scale, all the way through to core scale. Then we have discovery, so that's mainly exploration geophysics. Sustainable mining technologies, that's the program I'm from, and that's what I'll be talking about mainly today. Sensing and sorting, so that's pre-concentration, and that was the next door technology, for example. And then mineral processing, so that's across all commodities, so iron ore, coal, lithium, magnesium, basically developing hydromet, pyromet, all different technologies to optimize the processing flows. So let's focus on the technologies that I'll talk about. Everything I'm talking about today was done in collaboration with partners. These are some of the key partners of the projects that I'm presenting on today. Both national and international partners, as I said, is key. And there's Boeing and NASA collaboration that's related to the aerospace and the space stuff that I'll talk about at the end. And these are some of the current commercialization licensees that have licensed our technologies. So these are the priority areas for CSIRO mining technologies, and just having a chat to Jamal and the colleagues last night at dinner, there's so much synergy in terms of potential collaborations here. So geotechnical monitoring and modeling, geophysical sensing, mine ventilation, personal dust exposure. That's a big issue in Australia at the moment, particularly when it comes to respirable crystalline dust. Gas drainage design, frictional ignition and SPONCOM. We've had a couple of recent incidents in Australia that have brought that to the fore. And stockpile cavity detection, not just for coal stockpiles, but for all commodities. Then in terms of mine efficiency R&D, mine automation, particularly in explosive or extreme environments, blast hole radar, excavation and drilling, ground penetrating radar systems, inertial navigation-based solutions, and finally in environmental sustainability, emissions abatement and green steel, mine wastewater treatment and reuse, tailings management, mine closure and remediation, and climate adaptation. So I will touch upon a few of those examples in this presentation. There's a number of different laboratory facilities that support this research. I don't have time in this presentation to go through them, but a couple that I will sort of focus on this is the CSIRO drill core laboratory. This one is actually located in Perth. And this is basically building up a database of core, both legacy core as well as new core, using different technologies. So XRF, XRD, optical, hyperspectral, to try to get more value from those core databases. This is based in Brisbane at the Pullenvale site. So this is the rock cutting lab. I was very interested to visit the facilities that Jamal took me through at EMI. Once again, lots of overlap here. Linear rock cutting rig, similar, Jamal, to what you were showing us. This one is really being focused at the moment on frictional ignition. So once again, we've had a couple of incidents in underground coal recently. Frictional ignition, the standards that are being used are quite old, decades old, and essentially the client is wanting CSIRO to revisit those standards, get a better understanding, and potentially update best practice in that field. And then there are other rigs there in terms of the excavation and cutting research and full size drill rig. This is our rotary cutting test rig as well. And a number of facilities specifically focusing on pick design and pick wear. One of the technologies that CSIRO has been working on has been thermally stable diamond composites for both longwall shearers, continuous miners, as well as hard rock excavation. So these facilities are focused on understanding those properties. So design and simulation. This is work that we've been conducting with Rio Tinto and University of Queensland. And one of the big challenges, as we all know, is the pressure has always been to transform mining into a manufacturing industry. How many years have we heard about this? Manufacturing have productized. Why can't mining do the same thing? The fundamental problem, of course, is geological uncertainty, and that doesn't go away. So one of the things that we've been working on is trying to come up with formal frameworks to track that uncertainty. And this is a framework that originally was developed by Rio Tinto, and they wanted us to basically develop the maths behind it to make it a bit more robust and more rigorous. And it's called the reliability module. And what it allows you to do is quantify the reliability of each of the inputs into a design. Now, they were particularly interested in slope designs for large open pits, but it's actually transferable to underground, to tailing storage facilities. And what it allows you to do is use appropriate maths to take uncertainties. For example, if you've been performing some kind of stochastic modeling and you want to quantify how does that uncertainty feed into the overall slope design process, this framework allows you to do that. So these kinds of systems-based approaches, I think, are very important because so common in mining, we solve the problem in a compartmentalized way, not necessarily optimal from a systems engineering point of view. And when it comes to simulation, CSIRO has been working in collaboration with Geoscience Australia and Idaho National Labs, in fact, to try to come up with a multi-physics simulation for complex mining problems that can be highly parallelizable, so that you can deploy it on not hundreds of nodes, but tens or thousands of nodes. So you can run enough simulations, enough scenarios to start to fill out the uncertainty space. And this particular work has been developing geomechanics and coupled physics modules for mining applications using a framework called MOOSE, which is the Multi-Physics Object-Oriented Simulation Engine, developed by Idaho National Labs for the nuclear industry. But because of that, it's highly sophisticated. It's an extended FEM code, so it's not a discrete code, but nonetheless, it's extremely powerful. This particular application was looking at mine surface and subsurface water interactions in the Hunter region in New South Wales. And it was a very complex problem due not just to the complexity of the geology, but also due to the complex interactions of the different water charge and discharge mechanisms. And so that's an example of where that kind of sophisticated multi-physics, but also highly parallelizable simulation can pay off. And then we do a lot of research on geotechnical analysis and modeling as well. Some of it is based on in-house code. Some of it is based on third-party codes, but particularly anything to reconcile continuum and discontinuum codes and to try to get continuity and understanding as the not just the scale of the problem increases, but the rock mass behavior changes. That's of great interest to us. So these are all areas that we're very keen on collaborating on. Spontaneous combustion, as I said, is very topical at the moment. So research on appropriate design of mine ventilation for underground coal to mitigate spontaneous combustion, as well as inertization strategies to mitigate SponCom is of great interest to us. And also from a environmental sustainability point of view, mine methane emission reduction, so for pre-drainage and post-drainage, as well as ventilation air methane destruction, which I'll talk about shortly. Then in terms of sensing and monitoring, we have been working in this space for a number of years in collaboration with others. This is an example of a current collaboration between CSIRO and CCTG, Chinese Coal Technology and Engineering Group, on seismic coupled with measurement while drilling. So in this particular case, we're wanting to use additional seismic monitoring, both on the rig as well as subsurface seismic monitoring, to provide additional parameters for improved inference on lithology detections, interface detections, as well as rock mass classification. And this is current work in progress. Borehole radar is another one. So this one here is basically using a bistatic radar coupled to the drill stabilizer and uses the drill string as an antenna. So it's a forward-looking radar. Now, the particular application of this one is a coal application because it's being funded by ACARP, which is the Australian Coal Association Research Program. But actually, the application is much more broad than coal. And in forward-looking mode, the reason why ACARP are interested in it is for achieving appropriate drill and blast standoff from the interface so that you don't get dilution. But actually, if you use that same technology in sideways looking mode, you have the potential to fill in those exploration holes, particularly with regards to geotechnical structures. And that's always been a big issue when it comes to cost effectiveness of building a highly detailed fracture network model for geotechnical purposes. So this one is currently undergoing field trials at the moment. And of course, there are in-seam applications as well. The other big area for us that we're focusing on is distributed sensing using fiber optics. And I'll just go through a couple of the examples of what we've been looking at. So we've been looking at deploying fiber optics in different operating mines to assess their efficacy in three fronts. One is for acoustic or microseismic monitoring. Second one is strain, and the third one is temperature. So what I'm showing you here is a distributed fiber optic network shown the horizontal and the vertical lines. So that was a horizontal network as well as a subvertical grouted fiber optics cable, coupled with I think it was 4 geophones as well, 4 triaxial geophones. So fiber optics has great potential for distributing microseismic sensor networks over scales never before seen, but it's essentially a uniaxial sensor. So what we use is we use the triaxial sensors to perform that calibration and also assess failure mechanism. But in this case, what we were monitoring is longwall retreat in underground coal mine and looking at locating microseismic events associated with fracturing and delamination. And there was very good congruence between location and microseismicity and the lithological layers, the previous knowledge about that rock mass condition. And this next one is a sublevel cave. So this is a copper deposit. And in this particular case, it was a network of subvertical boreholes. Once again, fiber optics distributed with geophysics, with geophones as well, but we're monitoring both seismicity and strain. And this one here was not just monitoring the fragmentation of the rock mass in the sublevel cave, but also the cave propagation as well. And the final example I'll take you through is block caving. So this is the most recent example where we've used a network of subvertical grouted fiber optic cables to monitor seismicity during cave propagation. And actually what you can see on the top left there against that 3D model, that grey 3D model, is a number of events detected in regions previously thought to be aseismic by the site. So it's through having that very dense network of seismic nodes, seismic sensing nodes, that you can start to detect things that you wouldn't be able to pick up with a sparse network. We've just started tailings storage facility monitoring program. So this is a research project to determine the efficacy of using the fiber optics approach for monitoring tailings dam stability. The big issue that we're testing here is the coupling. Of course, with all these seismic sensors, it comes down to the coupling. So the particular coupling methodology being trialed here is to install the fiber optic cable at the time of the infrastructure construction, so you can achieve good coupling with that infrastructure. And that program will be going on for the next 2 years to determine the efficacy of that. One of the big challenges with distributed fiber optics is the fiber optics is really cheap. You can use telecommunications grade fiber optics. The interrogators are very expensive. They range from between 200,000 Australian to 400,000 Australian. So divide by 1.5. But so what we're working on in collaboration with the government and the universities is a new facility based at the Brisbane site to test the ability of using silicon photonics to miniaturize these different geophysical sensing technologies. And the fiber optics interrogator is the primary target. If we can miniaturize the interrogator, we can improve not just its power consumption, but make it much more robust. And that has been one of the challenges also with distributing these technologies in mine sites, is they are fragile technologies. The interrogators are fragile pieces of equipment. And so essentially that's a class 10,000 clean room that will be set up with appropriate fabrication facilities to start to look at some of these silicon photonic circuits, if they can be coupled in packages, to then start testing in the field. Also in terms of sensing and monitoring, this is some research I'm leading in collaboration with CCTG in Chongqing, which is using vision-based systems for slope deformation monitoring. So traditionally in open pits, radar dominates now. It's normally terrestrial-based radar, but more and more mines are using satellite INSAR. But they suffer from line of sight bias, so they only see deformation towards or away from the sensor. And that can lead to actually quite dramatic misinterpretations, not just of the failure rate, but also the failure mechanism, because you can be attributing the failure to incorrect structures. So what the project here is about is to use low-cost vision sensors coupled with the radar to then provide 3D deformation vectors. And this project has been showing that. So we've been testing at 2 ranges, basically 100 meters and 1 kilometer. So that's a big challenge for optics to deal with the 1 kilometer range. But we've shown that at 100 meters, you can achieve millimetric precision, which coupled with the sub-millimetric precision of the radar is more than sufficient. And at 1 kilometer, you can certainly get better than 10 millimeter precision, probably a few millimeters, depending on the algorithm. So this is a work in progress, but it has potential to basically address a big issue with slope deformation monitoring. And then the next topic is navigation and excavation technologies. So CSIRO is in the process of commercializing a navigation technology known as LASK, developed for longwall automation, to basically ensure that longwall shearers maintain appropriate lines and orientations throughout the cut. It's currently deployed in quite a few mine sites, about 60 to 70% of Australian mine sites, a number of US mine sites and Chinese mine sites. And what we're trying to do now is broaden the adoption of this technology to other parts of the mining value chain. Also fundamental to that technology is the X-scan system, which is a LiDAR system that's contained in an explosion-proof enclosure. So the optics of that enclosure are such that, and the algorithms are such that the LiDAR produces a distortion-free corrected view of a real-time view of the space. And so now we're adapting that technology to support continuous miners. There's a huge opportunity there to, particularly in countries like India, where automation of continuous miners is quite promising, and also shuttle car navigation. So what you're seeing on the screen here are some recent trials on shuttle car navigation using this system. So that's always been a big challenge, because shuttle car collisions with roadways are quite common, very narrow confined areas. And you can see on that image in the center there that the offline drivage associated with the shuttle car, once this system is engaged, can be improved quite dramatically. And then, as I mentioned, we are also researching on different PIC designs, and also thermally stable diamond composite coatings for PICs. A number of different cutting heads and use cases are being trialled in that laboratory facility that I spoke about earlier on in the program. And there's currently a major trial of this happening in China as we speak. And then human health and environmental sustainability. So one of the big issues when it comes to RCS has been the turnaround time associated with getting the sample from the personal dust monitoring system, applying the analysis, and then providing those results. So CSIRO has been working on a system to provide rapid on-filter analysis for those dust samples. And this is a collaboration with the Australian industry as well as with international partners. And these results are currently being trialled as well to determine if the precision of that analysis can be supported with this rapid turnaround time. And in terms of methane mitigation, another technology that we've been working on is known as CATAVAM. So this basically, in the Australian context, ventilation air methane makes up 15% of our total methane emissions. So it's a major problem, but of course it's not unique to Australia. So we're hoping this technology can be adopted worldwide. But in contrast to traditional RTOs, or regenerative thermal oxidizers, this is a catalytic-based approach. So this can actually reduce the temperature associated with an RTO operating at a coal mine for destruction of ventilation air methane by almost a factor of 2. But not only that, it can target much lower methane concentrations. So in Australia, we have very good pre-drainage. So our ventilation air methane is typically below 1% and can be as low as 0.2 or even 0.1%. So destroying that very low concentration methane is always the challenge. And recent trials at an Australian mine site have shown very encouraging results. So once again, this is a collaboration which is currently going through an expression of interest for commercialization and scale up. The trials to date have been performed on 1 cubic meter per second. The next level scale up will be 10 cubic meters per second, and full scale will be 100. In terms of the waste reuse and utilization, one of the teams at CSIRO has been working on electrochemical mineral carbonation. So using mine waste, typically mafic or ultramafic waste, as a source, as a sink, I should say, for CO2. So this involves, unlike traditional leaching processes, this involves a lower chemical, lower energy pre-treatment, electrochemical pre-treatment of that waste. It's only bench scale, laboratory scale at the moment, but basically to prime that waste material to act as an appropriate mineral carbonation source. And so far, the results have been quite encouraging. It's only low TRL, laboratory scale, but this is another exciting area for us. And then in terms of mine water remediation, so for a number of years, CSIRO has been working on mine wastewater treatment in collaboration with the universities as well as the industry sector. And there's a number of different technologies that have been developed there. Unlike just using traditional reverse osmosis, it's a coupled forward osmosis, reverse osmosis, and depending on the type of water being treatment, a membrane-based distillation crystallization process as well. And this has been shown to be able to deal with very high contaminant as well as brine and acidity levels in terms of the mine wastewater. But interesting offshoot of this research has been the implementation of this technology for regional settings. So a big challenge in Australia is our regional communities, particularly our Indigenous communities in Australia, quite often suffer from very poor water quality. The infrastructure investment has not been made there in those regional communities for appropriate water treatments. And so currently this same technology, the same approach is being developed with Indigenous partners to use to trial for those wastewater treatments or human water consumption treatment use cases as well. And the other thing that we're very interested in is using nature-based resources to form some of the composites that are used in the treatment as well. So once again, trying to address this circularity side of things. And then there's also, CSIRO has been working for a number of years in mine backfill approaches, as well as closure and remediation monitoring. So we actually have quite a sensitive area in one of the suburbs in Brisbane, which is built upon legacy mines and is suffering subsidence. So CSIRO is working with the government. We've been monitoring that site now for over 15 years and also developing strategies to try to mitigate some of the ongoing subsidence going forward. But this is also quite relevant to one of the priority areas for us going forward is to get more involved in tailings management research as well. So some of the facilities that we've used for the backfill research are going to be repurposed for tailings research. And in particular, we're in the process of setting up a tailings research laboratory at the Brisbane site. And this is quite an exciting time for us in that respect. And then also in terms of emissions mitigation, some of those honeycomb monolith structures that have been developed for methane capture, variants of that can also be used for CO2 capture. And we're currently developing, as part of a green steel initiative in collaboration with other parts of CSIRO, techniques to capture CO2 from blast furnaces and basically convert that CO2 into CO, which is then a reductant for the blast furnace process. So reducing not just the emissions of CO2, but also the coking coal requirements as well. There's also quite a big team involved in dewatering and recovery. So we actually have a laboratory there that's traditionally been focused on flotation research, particularly for coal. And that's the sort of plate membrane, as well as dense medium cyclone, a number of different technologies. And so we're focusing that facility now on investigating different tailings dewatering approaches. And one of the potential benefits of that is reuse of the tailings material and in particular geopolymer composites and geopolymer flows as well. So that particular research team has been developing different techniques to perform online QA/QC of the slurry prior to forcing it into the geopolymer flow, and then testing the performing geotechnical testing of the geopolymer to see what its potential uses are for different construction use cases. One of the interesting use cases is to use the geopolymer itself as shoring up tailing storage facility embankments as well. And finally, I'll just finish off with some of the aerospace applications. So this is kind of an example of mining technology developed for mining being translated to other industries. I didn't mention it, but the methane mitigation technology, that's actually being trialed in the agriculture space as well, and the farming space, particularly with animal feedlots. So the ability for it to destroy diffuse methane from cattle feedlots as well. This is another example of taking a technology. I mentioned the CSIRO vision technology I was involved with many years ago, photogrammetry-based technology, and using those computer vision techniques for other applications. We've been working with Boeing for a number of years to develop a system to support high precision metrology of robotic end effectors. And in particular, they require very precise 6 degrees of freedom localization of the end effector to develop automatic paint livery system deployment. Essentially, they want a giant robot to paint their aircraft. And it's quite a challenging problem, not from a safety point of view, but from an aesthetics point of view. Any small errors in the robotic end effector can show up in the livery. So what you see there is an example of a test vertical stabilizer. That's this center one over here. That's on an Alaska airline. So that's actually currently flying at the moment, and that was developed with the system. And then we've also been working with Boeing and NASA to take technology that was originally developed for mining. In particular, we developed a stereo camera system for continuous online pick monitoring for cutter heads, and combined that with the Wildcat SLAM technology that's in the HoverMap and Emerson technology to develop a payload for mapping in the internals of spacecraft. And that's what this shoebox size payload is. So that's on the International Space Station at the moment. So this is just a closer view of that livery deployment technology system. And actually, my trip this time to the US, I'll be heading to Seattle to work on this particular project. And this is the payload that was launched to the space station and is currently operating on a NASA robot. That little cube that you see there is called the Astrobee. It's a NASA Ames robot, and our payload on the left plugs into the robot and scans the environment. But anyway, it's a cool example of mining technology being used for something completely different. But CSIRO more generally is very interested in investigating how can we take technology, something that mines is very interested in as well, that's traditionally been focused on one domain, and apply to something with very different constraints. And I think in situ resource utilization, which is a big area of focus for NASA in the US, is a potential area of future collaboration as well. So yeah, thank you for your attention. I've ripped through all of those. I was saying to Jamal that if there's any particular areas of interest, I'm very happy to get additional slides and context for key researchers as well. But the key message I want to say is that very good opportunities for collaboration, but also anything of impact in my career has always happened through collaboration, and quite often international collaboration. So thanks again for the opportunity to present today. Thank you.
You're pressed against the time, but if you
Mark,
press the
how long
button,
are you here? Are you here this afternoon and tomorrow?
he's heading to the airport right after.
Right after?
We can follow up though.
Okay, I have some ideas.